Hi! So a couple weeks ago I made this video where I, as a pretty established competitive programmer with basically zero experience in interview stuff, took on a bunch of FAANG questions to see how it would go. And in that video I promised that if I got 1,000 new subscribers that I would make a video covering my thought process and solution to each of those questions. And wow, did we blow past that goal. So this is that video. Enjoy. If you haven't seen the questions yet and you want to try them yourself, they're in the description, you can check that out. And for each question, I'm going to explain my thought process and try to explain it in a way that you can understand how I came up with the solution, instead of just throwing the solutions at you, because that's not helpful. And of course, I'll also explain the solution, and for the questions where there's a better solution that I didn't come up with, I'll explain that better solution as well. And that's all for the intro. Let's get started. Okay, so this is Facebook. Again, link is in the description, and let's start with a summary of what the question asks. So you're given a grid with zeros and ones, for example, like so. And zeros essentially represent water, and ones essentially represent land. So for example, if I draw out water here and land here, then you can see that the water will separate the land into a bunch of different islands. And these islands are connected via the 4 cardinal directions, like north, east, south, west. Your goal, or you're able to change a single 0 to a 1. So for example, I can change this water into land. And your goal with this change is you want to make the largest possible island with this single change. So for example, if I change this, then this entire group will become an island because I sort of merge these 2 islands together. And this is the best we can do. So your goal is to make the largest possible island by making a single change from a 0 to a 1, or not. You can also not make a change. But your output is the size of said largest possible island. So the solution is complicated. So let's start with the basics. Let's start with just a brute force. So we brute force trying each individual change. So we change, for example, this water to land, and then we see what happens. Now, the way we can see what happens is we can run a DFS on the islands to find the size of every island and to group the islands together. So the complexity of this is there are O of n squared cells, which means that there are O of n squared cells we'll try changing, and because there are O of n squared cells, the DFS will also take O of n squared each time, meaning that the overall complexity is O of n to the 4th. So that's not great. So we want to be able to optimize that. So how can we do this? There are 2 things we can optimize. We can either optimize the cells we try, or we can optimize the DFS. So let's start by trying to optimize the cells. And you can think about this for a while, and you can try it. And you can try to reduce the number of cells that you end up checking. But ultimately, I'm not sure if it's possible. It's very annoying, it's caseworky, it's just really, really complicated. You're going to hate yourself after you try and write that solution. It's not worth your time. So let's just rule out trying to optimize the cells. So we'll say that the O of n squared for cells is fixed. So the only thing that's left to optimize is the DFS. So we don't want to DFS every time we make a new change. That's essentially the goal. But what we can realize is that when we change a cell, let's say for example we change this cell. When we change a cell, it only affects the islands that are directly connected to the cell we changed. So because this island is not connected to the cell we changed, this island doesn't change at all. It's still size 3. The only island that is affected is the island that is connected, which is this one. And now these islands merge and become this one. So how can we take advantage of this? Well, we can notice that if the island's going to be bigger from one of our changes, then the bigger island has to be merged with the cell that we changed. So it's enough to, every time we make a change, we only check the island adjacent to, or we only check the island that's connected to the cell that we changed. So if we can figure out how to do that quickly, if we can quickly compute the size of the island that's connected to the cell we changed, then we can have a better solution. So let's figure out how we do this. In this simple case, let's say, for example, we're just considering changing some cell, then a simple method we could try is taking the sum of the sizes of the adjacent neighbors. So for example, here, if we're considering this changing this cell, then there's an island of size 2 to the left, and there are no other islands to the rest. So we have a land of size 1 here, and we're merging it with an island of size 2, which means the total size is 3, which is accurate for this case because we have these 3 cells. But the problem is when we try to change something else. Let's say, for example, we try to change this cell. Then here we have an island of size 0 above, 2 to the left, 3 to the right, and 3 to the down. But the problem is these are the same islands. So we do not, in fact, have a total island of size 9 because that would be absurd. Instead, we only have a total island of size 6. It's 1 plus 2 plus 3, not 1 plus 2 plus 3 plus 3. So if we have the same component, or if we have the same island in multiple directions, then we overcount the size of that island. So what we need to do is not count the same island twice. And we need to do that efficiently too, because if we, for example, say we encounter this island, then we need to make sure that we don't encounter any cell from this island again. But if we were to do that, it could be up to O of n squared again, because what if this island is huge? If we decide to mark all of the cells of this island as bad, that is, we can't add that again, then this could be O of n squared. It could be O of the size of the island. So we need to do it a bit more efficiently than that. But instead of dynamically on the fly marking every cell of every island to be bad if we encounter that island, instead what we can do is we can do something very common for these flood-fill BFS types of problems. We can give each component a number, or we can give each island a number. So say this is island 1 and say this is island 2. And then, so renaming these, we can, for example, say this is island 1, island 1, island 2, island 2, island 2, and then we have water everywhere else. So for example, here, 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 and here. And then that way, that makes it a lot easier now. Because now, when we encounter this cell, if we encounter a 2, then when we encounter a 2 again, we can check the islands that we've already added, and we can just say, hey, we already have a 2, let's not add 2 again. So as an example, when we do this, we'll have no island above, we can have a 1 here, so we can keep a list of the islands that we've already encountered. And then when we encounter a 2, we can put 2 in the list, and then when we encounter a 2 again, we can see the 2 is already in the list, so we don't add it again. And this works. This will work, because now we count the sizes of the adjacent islands, and so we sort of merge all the adjacent islands into a big island, but we don't overcount the same island multiple times. And keeping a list and just checking that list when we want to see if we've already added an island is simple. That's the easiest way to do it. There is a slightly better way that cuts off like a factor of 4, and I do that in my solution, but I'll leave that to you as a challenge to figure out because it's not really that important. Already we've reduced this DFS to O of 1. Or this extra check to O of 1, because now we're only checking the 4 adjacent neighbors, and we're just adding the sums of the sizes of those islands together. So instead of O of n to the 4th, now we have O of n squared total. And since the size of the input is O of n squared, we can't really do better than that, so this is optimal. O of n squared is optimal, this solution is optimal. So to recap, we try changing every cell from a 0 to a 1. We try every cell. We see what happens when we change it. And to find the size of the island of the cell we've changed, we take 1 because we changed that from a 0 to a 1, and we sum up the sizes of the islands that are adjacent, except we have to take care of the special case where we cannot add the same island more than once, so we keep track of this list of the numbers of islands we've encountered, and don't add it again if we already have. And the way we assign these labels can be done with just a simple DFS or BFS, And we can also pre-compute the sizes of each island given the labels. So for example, we can say that island 1 has size 2 and island 2 has size 3. And then we can that's how we can easily find out the sizes given the labels. So yeah, there you go. So here's what my code looks like. Essentially, we start off by initializing some stuff, and then for each cell, we start by doing a DFS to label its component. So we have this variable C, which represents our current component name, and we run DFS to, in each case, we essentially label the component of, or we give each cell its component's label, and then we DFS to adjacent cells, and we also keep track of the size of every component. And then once we've labeled all the components and we found out all the sizes, then we check each cell and try to change it from a 0 to a 1. So here we only process the zeros. Then we look at the neighbors, and this is my way of essentially making sure we only add unique components so we don't add the same island twice. And then we update the answer, and then, yeah. So we run DFS, and then we try changing each 0 to a 1 efficiently. And that's basically the solution. Okay, this is Apple. Here's the question. Essentially, you're given k linked lists, each of which is individually sorted. So each list within itself is sorted, and you're given k of them, and there are n total elements. Your task is to merge each of these linked lists into a single mega sorted list. So for example, like this. And that sorted list should also be a linked list. So essentially you need to move the pointers around to create a mega linked list. So there are two different solutions that I'm going to go over. The first of which is the solution I came up with, and because it's very simple. So let's take a very simple approach. Find the smallest element out of all of the arrays and make that the first element. So in this case, the smallest element could be either of these ones. So we take that element, make it the first element, and then we remove it from the array, and then now we have the rest of the arrays. And note that because the arrays are sorted, removing the smallest element will not change the fact that they're sorted, so the arrays will always be sorted. And because they're sorted, we can take the smallest element every time, and we know that there's not going to be any smaller element because the arrays are sorted. So the smallest element is guaranteed to be the smallest element out of all of the arrays. So we can take the smallest element, remove that element, and then do it again. Find the next smallest element, put that in the list, remove that, and then find the next smallest element, put that in the list, remove it, find the next smallest element, and etc. And this will work. But the problem is the process of finding the smallest element every time is O of k, because we have to go through each of the lists, and we have to look at the smallest element in each of those lists, and then take the smallest element out of all of those. So this is O of k, and it's O of n times k because there are n elements, so we have to do this process n times. And because k can be up to n, because we can have just n one element lists, this can be overall O of n squared, which is pretty bad for a sorting algorithm, because just naively sorting, like just merging all the lists together and then sorting that list, will take O of n log n. So we should definitely be able to at least achieve n log n. But it turns out we can do better, because this O of nk solution can be optimized pretty well. Because note that when you consider the smallest element of each of the lists, when you remove one of the elements, only one of the arrays changes, specifically the array that you chose the element from. For the rest of the arrays, the smallest elements are still the same. So really, what we need to do this efficiently is a data structure where we have fast, we need to find the minimum quickly, so we need fast find min. We need to then delete the minimum out of our data structure, like so, and then we need to insert the next smallest element inside that data structure. So we need fast find minimum, delete minimum, and insert. And this is basically exactly what a heap does. A heap does all these things quickly. find the minimum is log n, delete min is log n, insert is also log n. And maybe it's O of 1, I'm not actually sure. But the point is, a heap will do all of these quickly. And because there are at most k elements in the heap at any time, each heap operation is O of k, or sorry, O of log k. So in total, instead of O of n times k, it's O of n times heap, which is log k. So O of n times log k is our final complexity. Yeah, so that's it. We select the smallest element, and then we optimize selecting the smallest element, because that's really the only thing we can optimize, because we have to process every element n times. So the only thing we can optimize is this k factor, and therefore that's what we do. We optimize it using a heap. Yeah, so this is my solution, but there is in fact a better solution. Better in the sense that because I'm storing k elements in a heap, the memory usage, memory does not spell like that, the memory usage is O of k, which again can be up to O of n, which is pretty bad. So we can do better. And the way we can do better by just using less memory is very simple, in fact. Very simple and very convenient to explain, because all we need to do is merge sort. Yeah, we just do merge sort on these lists. Straight up, just do it. If you don't know what merge sort is, it's very common. Just search it up. I'm not going to explain it here. But yeah, just do merge sort. It's O of n log k because there are k lists, and that's just how merge sort works. There are like log k levels of merging. And it's O of 1 memory because merge sort is in place. And all we're really doing is moving the pointers around to merge the lists. Yeah. Honestly, I should have seen this coming because it's kind of exactly what merge sort is anyway. We're merging a bunch of sorted lists. And yeah, that's basically it. Although merge sort might honestly be more tedious to code, so it's really up to you which one you want to use. But yeah, that is it. So here is my code that uses the priority queue stuff. Basically, in the beginning, we insert the beginning of every list into the priority queue. And then while we still have elements in the priority queue, take the smallest element. Note that because I'm sorting by greater, since C++ priority queue normally takes the largest element, but because I'm reversing the operation, making it sort by greater will actually make the smallest element be on top. So the top element is the smallest. Then we create a list node for it. We update the list that we're maintaining, and then we just add that element to the list, and then add the next element of the list we chose from to the priority queue. And that basically works. You can optimize the memory a little bit by like deleting the node that we removed from the list. I think, I'm not actually sure. I'm pretty sure that would optimize memory a bit, but it still wouldn't be as good as just straight up merge sort. So it's really up to you. Okay, this is Amazon's, and here's the question. The question itself is simple. You're given a number n, and you're asked to find the number of ways to write n as the sum of some consecutive group of numbers. For example, 1 plus 2 plus 3, all of these are consecutive, or 4 is consecutive to itself, or 5 plus 6. And the rule is all the numbers have to be positive, so where's my cursor? Greater than or equal to 1, and consecutive. Right, so that's our start. So a common technique for these kinds of mathy questions is stick in an equation and see what happens. So we want to try and formalize it and potentially make it simpler to approach by writing down an equation that represents our question. So we can try and find sort of a formula for the sum of consecutive numbers. And then we can set that equal to n and then see if that makes it easier to count the groups of consecutive numbers. So how do we find this formula for the sum? We can start with an example. Let's say we do know the formula for the sum of triangular numbers, which is to say 1 plus 2 plus 3 plus etc. up to n. The sum for that is n times n plus 1 over 2, and I'm not going to explain that here because there are probably a lot of better videos on the internet that explain that. It's a very common formula, but the point is this is the sum. And the reason this is handy is because these are consecutive. So what we can do is, let's say we're trying to find the formula for like 4 plus 5 plus 6 plus 7, for example. What we can do is we can subtract out the triangular numbers. We can subtract out 1 from the smallest, we can take out 2 from the second smallest, 3 from the third, and then 4 from 7. And then we end up with 3 plus 3 plus 3 plus 3. And these are two things that are very easy to find, because now we know these are triangular numbers. So this is 4 times 4 plus 1 over 2, and this is just 4 times 3. So that's nice, right? So that's our general strategy for finding this formula. So we want to essentially generalize it and make it work for any group of numbers. So how do we do that? Let's say there are y numbers. Or let's say there's a group of y numbers that starts at x. So for example, x plus 1 plus x plus 2 plus ... plus x plus y minus 1. So in total, there are y numbers. Numbers does not have two e's. Yeah. So let's break this down. Again, we can subtract out 1 plus 2 plus 3 plus ... plus y to get x minus 1 plus x minus 1 plus ... And ultimately we end up with, what do we end up with? We end up with x minus 1 times y, that's this part, plus this part, which is y times y plus 1 over 2. And we want this to be equal to n. So let's try setting it equal to n. And now we want to count the number of valid pairs of x and y such that these are equal to n. But the reason this formula is nice, the reason this formula helps us, is because this part of the formula is O of y squared. In particular, it's like y squared plus y over 2. And the reason that's nice is because let's try and think about when this formula is guaranteed to be larger than n. If y squared plus y over 2 is larger than n, meaning y squared plus y is larger than 2n, this will happen around y is equal to square root of 2n. So when y is larger than some number on the order of square root of 2n, then we can guarantee that y is not valid because it's too big. Because this number is going to be guaranteed to be greater than n, meaning that whatever value of x we choose, the formula is already going to be invalid. So all of that means that there are only about square root 2n possible values of y. There's a square root n amount of distinct lengths we could try. So we can iterate over y. We can iterate over the length of the sequence. And yeah. So let's make that happen. So when we iterate over y, we can assume that y is a constant. So let's say iterate over y. Iterate over y, meaning y is a constant. And we can plug this formula in again, x minus 1 times y plus y times y plus 1 over 2 is equal to n. And we know y is a constant. So what we want to do is, for a particular y, we want to find out, is there a valid x? Yeah. So to find that out, let's try and isolate x. Let's try and isolate x as a function of n and y, because then we can figure out what we need to do. So let's just mess with this equation. X minus 1 times y is equal to n minus y times y plus 1 over 2. And then ultimately, x equals 1 plus this whole thing, n minus y times y plus 1 over 2. Okay, this is messy as hell. just separate that out. N minus y times y plus 1 over 2. All that over y, because we divide out here. And then there we go. So now we've isolated x. So now what do we need? What constitutes a valid x? Well, by the constraints of the problem, it has to start, all the numbers have to be positive. So x has to be greater than or equal to 1, because otherwise if it starts at 0 or something, then that's just not valid. And also, not only does x have to be greater than or equal to 1, x has to be an integer, because if we could use non-integers, then literally every sequence would work. So we can't do that. We have to use integers. So x has to be an integer. So this first part is easy. For x to be greater than or equal to 1, we can just plug this into this equation. And then we subtract 1 from both sides, and we end up with this quantity, n minus y times y plus 1 over 2 divided by y, must be greater than or equal to 0. We can multiply both sides by y, and we can just sort of get rid of this part because we just can. Because yeah, we can multiply both sides by y. So ultimately we end up with n minus y times y plus 1 over 2 is greater than or equal to 0. Because again, we multiply both sides by y, and it just cancels out. So that's our first condition. And x has to be an integer. So 1 plus n minus y times y plus 1. I'm going to box this out, by the way. Nope, that's horrible. Over 2, close paren, over y, must be an integer. So the 1 doesn't matter because the 1 is already an integer. So essentially, this part has to be an integer, which means this quantity, n minus y times y plus 1 over 2, has to be divisible by y. And the way to measure divisibility is by using mod. We can say that this quantity mod y has to be 0. Because that's sort of the definition of divisibility. If this mod y is 0, then that's divisible. So ultimately, these are our two conditions. This quantity mod y must be equal to 0, and this quantity has to be greater than or equal to 0. So for there to be a valid x, the stuff circled in green must be true. And if that's true, then this y is valid, and therefore we can add 1 to the answer. And if not, then there is no valid x for this y, so we can stop. And if whenever this value, this quantity of y gets too big, whenever this is already negative, then we know that there's no valid, then we know that that value of y and any larger value of y is not going to work. So automatically we can be done. So those are our conditions. And here's my code. Ultimately, it's very simple. Instead of calling it y, I called it x, which might actually be a bit confusing. But you can just treat this as the value of y in our math. So while this quantity is less than or equal to n, because again, if it's greater than n, then it's guaranteed to not work. Then if n minus x times x plus 1 over 2, mod x is equal to 0, then that means that this condition, the divisibility condition, is satisfied, meaning that we can increment the answer. And this condition is guaranteed to be satisfied since we're checking it in this loop. So essentially, that's it. The code is extremely simple, but the math is not necessarily that simple. And yeah, ultimately, these are the conditions we're checking. So there we go. Okay, this is Google. This question may seem a bit complicated, but it's honestly fairly simple once you get to know it. So essentially, you have an array, like so, and you're going to pick some starting point and do some jumps. For odd jumps, you're going to look for the smallest value that's to the right that's greater than or equal to your current element's value. So the smallest value that's greater than or equal to current. And for even jumps, so in this case, the smallest value would be here, if this were an odd jump. And for even jumps, you're looking for the largest value that's less than or equal to your current value. Like so. So for example here, and it also has to be to the right. To the right. And here, for example, this would be the 2. Or no, sorry, it would be directly to the 3. Yeah. So what you're going to do is you're going to make these jumps, and then once you finish these jumps, you're going to make these jumps. So for example here, for the 4, you would jump to the 5, and then you would jump to the 3. And then eventually you'll get to a point where you cannot jump anymore. And the question is, are you at the end of the array or not? If so, then if you can get to the end of the array, then it's considered a good starting point. And if you can't, for example, with the 6, you can't go anywhere in your first jump, then it's not considered good. So the task is to count the number of good starting points. Yeah. So the very naive solution is to just try each starting point and hang on, let me get rid of these. The very naive solution is to just try each starting point and simulate the jumps until you get to the end. For example, here we have a 6. Where do we jump? We can't go anywhere. Okay, so this is bad. What about this 4? Here we can start off by jumping to the 5 and then to the 3. So this is good. For this 2, we can jump to the 5 and then to the 3. And then, so this is good. For the 5, we can't jump anywhere, so this is bad. And for the 3, we're already at the end, so this is good. And therefore the answer is 3. And overall, in total, this is up to O of n cubed because we have O of n starting points. For each starting point, we have potentially O of n jumps that we're going to make to the end. And it takes O of n time to find a jump. So that's the breakdown of our complexity. It is O of n cubed because there are O of n starting points, O of n jumps, and O of n time to find a jump. But it turns out we can optimize a lot of this. We can't optimize the starting points. There has to be O of n starting points. But we can optimize the number of jumps we make, and we can also optimize the time it takes to find a jump. So which do we start off with? I'm going to say this one because it's convenient. So we're going to start by trying to optimize the jumps. So the first thing we can notice is once we get to some position, we don't really care about the jumps that got us there. So for example, when we go from 4 to 5, we don't care about this 4 anymore. All we care about is that we took one jump to get here. And in particular, all we care about is that we're now on our even jump. We're now on the second jump and 2 is even, so there we go. And so because we don't care about how we got here, this 4 going to this 5 and this 2 going to this 5 are going to have the exact same answer. They're both on this 5 at an even jump. So the point being, when we start here and then we figure out the answer for this 5, which is yes, we can get to the end, then we go here and then we go to the 5, we don't have to refigure out the answer to the 5 because we already figured that out. We already know that 5 will lead us to the end. So this leads us to a solution with memoization. We can memorize the answer for each position starting off with an odd or even jump. So for example, for 3, for odd and even, it's a check because automatically we're at the end. For 5, for odd, it's a no because we have nowhere to jump. And for even, it's a yes because we can jump to the 3. And then same thing for here. For 2, for odd, it's a yes. For even, we have nowhere to jump, so it's a no. For 4, for odd, yes. For even, we can jump to the 2, and then the 2's even is false, so there's nowhere, no, sorry. For 4, we jump to the 3, so it is in fact correct. So even works. And for 6, odd is a fail, and for even, it doesn't really matter, but in this case, we would jump to the 5, and then we'd have 5 odd, which is invalid, so we can't go there either. So this can be done with memoization, or you can just directly do dynamic programming, which is what I ended up doing in my solution. But either way, we no longer have O of n jumps, because For each position, we care about exactly one thing, where we go next. And then we don't care about the rest of the jumps because the rest of the jumps will be handled later in the memoization. So ultimately, we have O of 1 jumps per starting point. So now instead of n cubed, it is simply n squared. So now what? We can also optimize the time it takes to find a jump. And yeah, so how do we do this exactly? Remember the definition of what we're looking for? We're looking for the smallest element that's greater than or equal to the current element that's to the right. Now, C++ has this very convenient feature called a set. And the set has a function called lower bound, which will find exactly that. If we ask for the lower bound of the value of current, it will find the smallest value in the set that's greater than or equal to current. So if we could have all of the elements that are to the right inside the set, when we need to find, for example, for 4, to find where we need to jump, we need all 3 of these elements inside the set. And then for the odd, we can use lower bound to find that we jump to the 5, because it's the smallest value greater than or equal to current. So if we can get ourselves in a position where we can use lower bound on the set of elements to the right, if we could have a set containing elements to the right, then we could find the jump in the time complexity of lower bound, which is O of log n. And to do this, we can do a special thing called a sweep line. We can iterate from right to left, and then we try processing element 3. And then when we're processing element 3, initially our set is empty, so we can't jump anywhere. But we can, however, note that this is the end, so it doesn't really matter. So we process 3, and then we find out where we jump from 3. In this case, it's nowhere for both odd and even. And then we put 3 in the set. And then we process 5. And now we look at the elements in the set, which is exactly 3. And then we can use this 3, we can use lower bound on this 3 to find where we go for odd. And then once we're done processing 5, we put 5 in the set and we continue. Then we go to 2, and for odd jumps, I just realized I made a mistake. 2 jumps to 3, not 5. But it doesn't really matter because it helped for our memoization example. Yeah, I'm probably going to get comments about that, but whatever. So now we have 3 and 5 in the set, and we can query the lower bound for 2, and we can find 3. And then we put 2 in the set, and then we continue. And then we process 4, we put 4 in the set, and then we process 6. And that's it. So if we sweep from right to left, then we could have, at exactly the moment where we need it, the elements to the right of our current element all in the set, and we can use lower bound to find the jumps. And to handle even, what we can do is, we need largest less than or equal to current. But what we can instead do is we can negate all of the numbers. And this is a very common trick when you work with sets. Negating the numbers will do exactly what we want. If we add, instead of 3, 5, and 2, if we add -2, -3, and -5, then largest now becomes smallest because all the numbers are negated, and less than or equal to becomes greater than or equal to. So with the negative numbers, we need the smallest number greater than or equal to the current. Lo and behold, that's exactly what we did with odd. That's exactly what lower bound does for us. Whoa, what did that do? Okay, anyway, so doing that will do exactly what we need. It's the exact same as odd. So by negating all the numbers, we can turn even into the same problem as odd, and therefore we can handle them both ways. Okay, anyway, so after all that, combining the sweep line with the jumps for each element, finding an n log n, the overall total complexity is n log n. And this is a pretty good n log n, or it is an n log n, but the problem is C++ set is in fact very slow. So in terms of runtime, this ends up doing very badly. It's like faster than 8% of submissions or something, so it's not very good. And there's a better way we can do it that works for all languages, because not every language has C++ set. So how do we speed this up? like complexity, or we can't speed up the complexity and log n is optimal, but there is a faster solution in terms of runtime. And the dp is O of n, so we can't really do better than that. But what we can do is we can optimize the part where we find the jumps. And the way we do this is by sorting the array. So for example, let's sort the array so that the array is sorted. That sentence is useless. And then we'll also keep track of the original indices. So this is index 0, 1, 2, 3, 4. And so 2 is index 2 in the array, 3 is index 4, 4 is index 1, 5 is index 3, 6 is index 0. And now, instead of looking for the smallest greater than or equal to our current, let's say our current is like 3, for example. Or no, let's say our current is like 4. So instead of looking for the smallest value greater than or equal to the current, because the array is sorted, now we're looking for the nearest, because the value now determines the index. So we're looking for the nearest value that's also to the right of current. But it also has to be to the right in the original array, because that's also one of our conditions. We can only jump to the right of our elements. So essentially, to the right in the original array means that the index in the original array has to be greater. So 3 has to be greater than 1. And the way we can keep track of this is we can treat these indices as values. So now essentially, we're looking for the nearest element with a greater value, or the nearest element with a greater index in the original array. And that can be solved via the classic solution of nearest greater element. I can't spell. With the classic solution of nearest greater element, which is a very common problem, not one that I'm going to explain here because, again, there are probably a million better explanations of it. So we're looking for the nearest greater element. We can solve that with a stack in O of n. And we can just find the nearest greater element for each element, and then we can use that to figure out where we jump for each point. So for example, for this 4, the nearest element with the greater index is this 5, which is index 3, so 4 would jump to 5. And we can do that for each element and figure out where they jump. So now the O of n log n, instead of being a set n log n, is O of n log n from sorting, which is much, much faster. Sorting is a very fast n log n, especially compared to set. So the runtime of this will be so much better. And the only thing that really matters, the only thing that dominates the complexity is sorting, since everything else is O of n. So yeah, it's going to be good. And that's basically the best solution I know of. Have fun coding this one. But in terms of my code, I did the set solution. So we initially create this dp array, and the ending elements should both be 1. So now for each element, we find the odd jump. So we invoke lower bound. And then if the jump is valid, then we update the dp array with the dp position of where we can jump. If where we can jump, specifically for odd, 0 is odd, 1 is even. So for the odd jump, if where we jump is valid when we start with an even jump, we can get to the end there, then that means that this should be valid. And then we add this element into the set so that future elements can use it and use it for the lower bound. And we do the same thing for even, except we just insert the negative values. So we essentially update the dp value using where we can jump. And then at the end, if the value is valid starting at an odd jump because we always start at odd, then we add 1 to our answer because it's a good position. And that's it. All right, so I would say this went pretty well. I definitely did better than I thought I would do on the questions themselves, and since I have more time to think through these explanations, I would say they came out pretty well as well. I think this will be a step up from my solution videos on stuff like code forces in the past because I get a lot more time to prepare on these and don't have to necessarily come up with stuff on the fly right after the contest. So yeah, hope you enjoyed and hope this was helpful and hope this can continue in the future. That is all. Goodbye.